So if we have a maximum tolerable acceleration for people on a subway train of 1.34 meters per second, and the stations are located 806 meters apart. So let's just draw that. We've got this over here, station A, station B, and the distance between them. It's always good to draw a diagram, is 806 meters. And there's some midpoint there at 403 meters. Okay, so that's our midpoint. So what's the maximum speed the train can attain between the stations? Well, it's going to accelerate up to that midpoint, and then it's going to decelerate from the midpoint to B. So what we need to do then is just say, well, if that's our case, we can our maximum acceleration is, and that should be squared, by the way, should be 1.34 meters per second squared. If we're accelerating at that rate and we accelerate up to 403 meters, what's going to be our velocity at that point? Because that'll be our maximum velocity at the midpoint before we start decelerating to get back into station B. So we can write down some stuff that we have. So let's say we have our initial velocity was 0, started from rest, and we start at some position of 0 meters. So we start at A, which is, we can arbitrarily say is 0 meters. Our acceleration 1 is positive 1.34 meters per second squared. And then we have another acceleration, which is our deceleration, 1.34 meters per second squared negative. Now, the distance, so x1, so at position x1, that's 403 meters at the midpoint. So that's some information. We want to find the velocity at that point. Do we have any other information? Well, we have that at VB, so at, we'll call that V2, that's 0 meters per second as well. So that's all the information we have. So we can use one of our equations of motion to solve that. Which one's it going to be? Well, it's the one that has all of our variables in it. And we are looking for the final velocity, V1. So we can use this equation that says V1 squared equals V0 squared plus 2AS, where S is the displacement. Remember, S is x2 minus x1, or, you know, delta x. You can call it whatever you like. Okay, so we are looking for V1, so we're going to have to square root both sides. So V1. V0 disappears because it's 0. 0 squared is 0. So we just get 2AS in here. So we can work out what that is. Now we can just put the values in. Square root of 2 times 1.34 times S, our displacement, which we started at 0 and ended up at 403, so that's 403. And that comes out to be 32.9 meters per second. That's the maximum speed, and it's the speed we reach when we're halfway between the stations. That's what we're asked for. And then we're asked for, what's the travel time between those stations? How long does it take to get between A and B? We can just use another equation of motion. So what we should do here is actually only because we've got two versions of acceleration, A1 and A2, we can't just put, you know, we have two equations. We can just say the time taken to get to the midpoint using acceleration, the positive acceleration, and the time it took to get to there, we just double that, and that should be the time taken to get the second half of the journey. So that makes sense from the symmetry of the argument. So we can then use the equation x1 equals V0 t1 plus half a1 t squared. That's basically just saying, you know, we find out the time it took to get to the midpoint, solving for t1 in this case. And then we just double that, and that should be the time taken for the entire journey. So we have to solve for, this is nice again, we get rid of our V0 t1. So we get x1 equals half a1 t1 squared. We want to solve for t, so we multiply by 2 and divide by a on both sides. So we get 2x1 divided by a equals t squared. So therefore, t squared equals, we can get rid of our squared here. And we can just say t is equal to the square root, so find the square root of both sides, 2x1 over a. We can put values in. 2 times 403 divided by 1.34. That comes out to be 24.53 seconds. Now, that's T1, sorry. So the total time, big T, is 2 times T1 for the entire journey, which is 2 times 24.53. And that comes out to be around about 49.1. Okay, so that's the total. Now, if we have some dead time, so question C is asking for dead time. What happens when we have dead time in the station of 20 seconds? Well, our total time then, I'll call this one capital T1 here. It's going to be capital T1 plus 20 seconds dead time. So that's going to be 69.1 seconds. That's how long basically it is before. So you take off, you wait for 20 seconds in the station, you take off again. So for one iteration, it's 69.1 seconds. So then you can work out it's 803 meters for the displacement. So so let's call it S is 806 meters for the entire journey. So we can just say that velocity, average velocity, is the distance or the displacement over the time. So that's 806 divided by the time, which is 69.1. And we get a value for that of 11.7 meters per second. So you can see that that's different from this value here. That's the maximum value. So at some point along there, we reached a maximum velocity of 32.9. So instantaneously, we were 32.9 meters per second. But over average, we're only 11.7. You can see how the average velocity can be different to the instantaneous velocity. Okay, so now we're asked to graph those. So we're asked to graph the position, the velocity, and acceleration versus time. So we can start off with down here, we've got our position, x and t. So we can put some units here. That's 10, 20, 30, 40, 50, 60, 70 should get us through. And up here we've got 200, 400, 600, and 800. That's the units that we're kind of working with. So remember that we accelerated up to our midpoint, and our midpoint was around about the 400 meter mark, so around 400. And it took us around about, if you look at the up here, that took us around about 25 seconds. So roughly on our graph, 25 seconds we got to this position. So like that. And we did that in a fashion that was accelerating. So our position would look like it's going like this. And then in the next 25 seconds, around 25 seconds, so up to 50, we got to around 800. But we were decelerating, so our graph should start to be more concave like that. So that's what our position should have looked like. And then for the next 20 seconds, we pretty much did nothing. So the position didn't change. So that looks roughly like a good sketch of the position versus time graph. Now, if we do the velocity versus time, then basically what happened was, if we use the same units on the bottom here, 10, 20, 30, 40, 50, 60, 70, just write them in every second one, 10, 30, 50, 70. We accelerated up to 32 point, you can see here, 32.9 meters per second in the first, say, 25 seconds, so up to here. So the maximum we reached to was about 30 something, so that's 10, 20, 30. So in 25 seconds, we accelerated in a constant fashion, so our velocity changed linearly up to around here somewhere. And then in the next 25 seconds or so, we decelerated at the same rate, like this, roughly. So same slope, but in a negative direction. And then our velocity was 0 while we sat in the station. Now, we could just see this as being, this slope the slope just here is increasing. So that's why our velocity is increasing there. And the slope is decreasing here, so it's getting smaller as we go that way. So it's also getting smaller there. And we need to draw one more graph, which is the acceleration versus time. And we know basically that's pretty straightforward. We accelerated at 1.34 meters per second at the start for 25 seconds, and then we decelerated. So, well, it's probably best actually if we were to draw our axes a little differently here, like this, and make this 1.34, make this minus 1.34 down here. And again, same axes here, 1, 2, 3, 4, 5, 6, 7, so that's 10, 30, 50, 70. Yeah, so we would have gone for the first 25 seconds or so, like this. And then for the next 25 seconds, we would have been here. Okay, and then sitting around for it with no acceleration like that. Okay, so we've done plenty of that stuff now. You should be getting your head around how that works. So some numpties dropped a pipe wrench from some height at a construction site. It's dropped out of his hand and hits the ground with a speed of 24 meters per second. Luckily it hits the ground, not someone else. What height was it dropped from? How long was it falling? And let's sketch some graphs to show its motion. So we can write a couple of things down here. If we choose, let's just choose upwards to be positive. You could choose downwards if you like, but I usually choose upwards for some reason. So therefore our acceleration is going to be negative g, negative 9.8 meters per second squared, because it's against that direction. If that's positive, acceleration is going to be downwards, so it's going to be a negative value. Our initial velocity, 0 meters per second, it's dropped from rest. The final velocity is 24 meters per second. And we're trying to find out here the height. So we're looking for delta y. You can call that S if you like, displacement. Okay, so we have an equation of motion that links those things together. It's this one, v squared, so vf squared equals v naught squared plus 2as. Or if you like, I'll just rub that out and make it 2a delta y. Right, so we're looking for the delta y. So we need to rearrange this equation. Okay, so let's subtract v naught squared from both sides. So we get vf squared minus v naught squared equals 2a delta y. So therefore, we divide through by 2a on both sides and we get delta y equals vf squared minus v naught squared, all divided by 2a. That's just doing some algebra to get our delta y by itself on the side there. We can put some values in now. you'll notice up here that I have Vf equals 24 meters per second. Well, it should be minus 24 meters per second because it's in the opposite direction, it's downwards. Its velocity is going to be downwards, finally. So we get negative 24 squared, doesn't even matter really because you square a negative number and you get a positive number, minus 0, so we can leave that bit out, divided by 2 times our acceleration, which is negative 9.8 meters per second squared. And if I do that calculation, I get negative 29.4 meters. So if I started at an initial point of 0, y equals 0 at this point, and then I let this thing drop at this point, negative 29.4 meters, basically the ground, the velocity is going to be 24. So we could have made the ground 0 and up there positive, but this tells us then that it was dropped from a height of 29.4 meters. The next question we're asked is how long it was falling. Well, we can solve a very easy equation of motion, which is just this guy. The final velocity equals v naught minus at. Okay, that's just one of our equations of motion. And we just solve it for, so it'd be plus at, sorry. In this case, that's going to be minus g. So that's our equation of motion there. It's one of our equations of motion. And we want to find the time, so we can rearrange this guy. So we subtract v naught from both sides. Vf minus v naught equals at. Divide through by a on both sides, and we get t equals Vf minus v naught over a. Therefore, t is Vf, which was negative 24 meters per second. Should probably put the units in at this stage because it just makes things messy, so just leave it as a number. Over the acceleration, which is minus 9.8, and I get an answer there of 2.45 seconds. Comes out to be a positive number, as it should, times positive. Okay, so it only leaves us now to draw the graphs of the motion. Okay, so we can do that by drawing our axes like this. This is time, and this is position y. And here, probably should put the units in meters. So we start from this point here at the origin at 0. And after around about 2.5 seconds, so we can have 1, 2, 3, so 1, 2, 3 seconds, it reaches a limit of around 30, negative 30 meters. So this is negative 30 here, negative 20, negative 10. Okay, and this thing, if you look at the equation of motion that looks at the position as a function of time, the one that we solved before, it's a quadratic function. So it basically looks like this. So at this point, here at 2.45, and it reaches the ground at around 29, you're going to get this this sort of thing happening with the position as a function of y. Let's do the velocity as a function of time. Again, the thing is going to initially start from 0, so after 1, 2, 3 seconds, it reaches a maximum velocity of 24 meters per second after this 2.45 seconds. So this is 1, 2, 3, so 10, 20, 30. It reaches a maximum velocity of 24 meters per second after 2.45 seconds. So, like that. And that's because it's constant acceleration, It should just be a linear velocity like this. So these are just rough sort of hand wavy ways of drawing these diagrams, just by considering the stuff that we just calculated before. So acceleration in meters per second squared is the next one. And because this is free fall acceleration, it's constant acceleration, then that's 1, 2, 3. It just remains minus 9.81 constantly, and then hits the ground, and still has acceleration of gravity acting on it. So that's that section. Easy peasy. Let's do another problem. So this is an example of using the graphical integration that we've seen a few times now. And we can just take this acceleration versus time graph and work out the velocities. As we're asked to find the difference in velocity between the helmeted head and the bare head in a collision with a soccer ball. So when a soccer ball is kicked towards a player and the player deflects the ball by heading it, the acceleration of the head during the collision can be significant, and these are the graphs of that as a function of time. You can see the time in milliseconds on the bottom scale there. So it measures the acceleration of a soccer player's head for a bare head and a helmeted head, and we want to see, so starting from rest, so the ball hits the head and something accelerates the head, we want to see what happens to the velocity of the head by doing the integration of this graph. So the scaling on the x-axis, this is 200 up here. So this will be 100, you know, and they're going to be 20 meter per second squared increments. And so at time 7 milliseconds, which is here, we want to see what's the difference in speed acquired by the bare head and the helmeted head. So we're just going to have to integrate under both those curves. It's a bit of a pain, but we'll get through it. So we want to find, for the bare head, let's write that down. Bare head. We just have to find this area. We need to find this area. That's a trapezoid. And we need to find that area. And then we need to find this triangle at the end. We need to find 4 areas. For the helmeted head, we need to find this area, this one, and this one. Okay, so we've just got to find 4 areas for those different regions. So let's do the bare head first of all. So we can use our, remember, I'll just write it up here, that the velocity, or the change in velocity, is the integration from t0 to t, the t0 to t1 of the acceleration versus time graph, like this. So it's just the area under the curve, just reminding you of that integral thing. Okay, so in we'll call this area A, this B, C, and D, and we'll call these red areas A, B, C, and D. Okay, so in A, red A, we can calculate the area of that guy. It's just going to be half base times height. So half the base, which is 0.002 seconds. So remember SI units, this is milliseconds, the base there, so we have to put it into to SI units. And the height is 120, okay, so up here. And that comes out to be 0.12 meters per second. Area B is the area of a trapezoid. And remember, the area of a trapezoid is going to be half the base times this height plus this height. Okay. That's how we work out that trapezoid. That's from previous problems. So we're going to get, in this case, half 0.002, and the heights, which is 120 plus 140, and that equals 0.26 meters per second. C, again another trapezoid, we just use the same arguments. It has an area of half, 0.002, 140 plus 200, which is 0.34 meters per second. And area D, finally, is just another triangle. Half base times height, half 0.002. And the base is, the height, sorry, is 200. Comes out to be 0.10 meters per second. So totally, we add all those up. We add that, and that, and we get 0.82 meters per second. So that's the change in the velocity from this point at here at 0, at 7 milliseconds, it's going to be 0.82. So the change in velocity is 0.82, and we just found that by finding the area under the curve. So for a helmeted head, we do the same thing. Okay, so we're going to get the area of that first triangle, which is half the base times the height, so half 0.003 in this case, times the height, which is 40, 0.06 meters per second. Area B is another, it's just a rectangle there, so it's just going to be 0.001. That's the width of it, and the height of it is 40 again. So that comes out to be 0.04 meters per second. Okay, and area C, another trapezoid, half the base, which is 2 again, 2 milliseconds. And we have 40 plus 80 for the heights on the trapezoid. And that is 0.12 meters per second. And one final area, area D, is another triangle with a half base times height. So I'll just erase that. Half base times height, so it's 0.001 milliseconds. So what? Sorry, 1 millisecond, 0.001 seconds times 80, and that is 0.040 meters per second. And we can add those all up. So we just add them all up and we get 0.26 meters per second. So that's just saying that the helmet is basically absorbing some of the acceleration, so that there's not as much velocity imparted to the head. And so the question is actually asking us, what's the difference in the speed? So we just need to subtract those from one another, and the answer then will be 0.82 minus 0.26, and that comes out to be 0.56 meters per second. That's the difference in the velocity from wearing a helmet to not wearing a helmet. I don't know a lot of soccer players that wear helmets, but maybe in future they will. Who knows? Okay, so we have one more problem that I'm going to talk to you about. This is a pretty easy one, but it's just, again, having a look at our equations of motion with constant acceleration. So a ball is shot vertically up from the surface of another planet. A plot of the position as a function of the time for the ball is shown in the figure here, where y is the height of the ball above its starting point and t equals 0 at the time the ball is shot. So the figure's vertical scaling set by 30 meters. So let's make that, so this is 30 meters here. This obviously then is going to be 5 meter increments. So 25, 20, 15, 10, 5. So we can redraw our scale. So what happens here is that in t equals 2.5 seconds, so at this point here, the ball reaches the top of its mark, okay, and then it reaches a delta y of 25 meters. And at the top of the mark, when it reaches the top of its mark there, then its velocity is going to be, its final velocity is going to be 0. So we're asking to find the initial velocity of the ball and what's the free fall acceleration of the planet. So first of all, we have to find what acceleration is. So we've got t, we've got f, the final velocity at the top there. Well, what we can do is call this, we can call that the initial velocity if we just look at this part of the fall. Okay, so from the top to the bottom, it's going to be symmetrical. So we can say, you know, it's falling from this point here. We can calculate what the free fall acceleration is. So now its initial velocity is 0 meters per second. So that helps us. Let's go with positive downwards this time. So we say downwards is positive. Okay. So then we're going to get a value for g basically, which is what the value on this planet of g is. So we're looking for our, well, what we're looking for here is the acceleration. Okay, so we look at all those things and we decide which one of our equations of motion to use. It's get rid of that. It's delta y, which equals Vf, keep saying V, sorry about that. It's y final minus y initial is V naught t plus at squared on 2. So delta y, which equals yf minus y naught, is equal to, this is going to disappear because V naught was 0, is equal to at squared on 2. We need to get the acceleration by itself, so we multiply by 2 on one side and divide by t squared. Okay, if we do that, we get a by itself. So if we multiply by both sides by 2, we get delta y, 2 delta y equals at squared. And if we divide through by t squared, we get a equals 2 delta y over t squared. We can plug some values into that now to get what our value for the acceleration is. Okay, and because we've taken downwards, we should get a positive value for the acceleration. So it's 2 times 25 divided by the time squared, which is 8 meters per second squared. So slightly less gravity than we have for that planet. Now the next part of the question is asking us for the initial velocity of the ball. Well, we've got our acceleration now. So if we take, something about this motion when we have free fall up and down is the velocity we headed up with is the velocity it'll end up with at the bottom. So if we started off with some initial velocity, shot it to the top, when it comes to the bottom, it'll get back to that initial velocity again. So we can look at this problem in a few different ways. We can just look at, if we wanted to, we could say it's launched from here upwards and it reaches, at some point it reaches a velocity of 0 at the top. So we'll do it that way. So that means its final velocity is 0. Its acceleration is going to be minus 8 meters per second, because we're taking this way as positive now. So I'm just showing you can change that around and get the right answer. Doesn't matter which way we say is up and down, as long as we consider the right direction. The acceleration is going to be down in this case, so we have to say a negative sign. So its final velocity is 0. We're looking for the initial velocity, so we're looking for v0 now. So what speed was this thing launched off at? What else do we have? Well, we have t. Takes 2.5 seconds to get to the top of the arc. And we have also, importantly, delta y, 25 meters. So, well, we could solve this with any number of our equations of motion now, but we can just choose one that's pretty obvious here, because we have this guy here, which is s. We can use the equation that says Vf squared equals V0 squared plus 2as, delta y, if you like. So we want to get the V0 by itself. So we just rearrange this. We can subtract 2as from both sides. So we get V0 squared equals Vf squared minus 2as, and then we square root both sides, so we get v0 equals the square root of Vf squared minus 2as. Now we can plug some values in. That's going to disappear because it's 0. We don't need to plug the values in just yet. We can just rewrite this as negative 2as. Okay, and this is going to be nice because we should get a positive value underneath that square root, which is imperative. Otherwise we get a complex answer, which you'll find out in maths. Okay, so if we put in the values that we have, we get negative 2 times negative 8 times the displacement, which is 25 meters, and it's upwards, so it's positive value. And if I plug all those things in, I should get an answer which is 20 meters per second. Okay, so I think by now, after doing all these problems, we should have our head around our constant motion equations, also how to get our accelerations from our velocity versus time graph and vice versa. So yeah, there you go.